itself.
So welcome everyone to the Hibiscus Coast Astronomical Society virtual meeting. For those of you on YouTube, the email that was sent out, so if you click on it, actually sends you to the YouTube page, but you can actually join the Zoom, which might actually be better because there are some connection issues going on here. Yeah, if you do that, just copy and paste the link. Don't click on the link, and then Chris will let you in on the Zoom side of things. This evening we're going to start off first off with Josh, who will be talking about the news, what's been going on up in space, and we'll then move on to Chris, who will be talking about open and globular clusters, which of course, as many of you know, is one of my favorite topics as well. So it's going to be a really good evening. So again, those on YouTube, if you go to the email or if you go to the Facebook group as well, the Zoom link is on both those places. You might have to copy and paste them rather than just click on them. So without further ado, I'm going to hand over to Josh.
Thanks, James, and welcome everyone. Thanks for tuning in, and I hope everyone is enjoying their lockdown and not going too stir crazy. I know myself, I'm quite jealous that the rest of the country's been able to go down to level 3, so they get to enjoy takeaways again, some KFC. Can't wait until we can enjoy that again. But in the meantime, here's some space news. We can hear about what's been happening recently. So I will share my screen. Make sure I get the right one. This one. There we go. So astronomy news. What's been happening above us? Hopefully you can see my screen properly. So first in the news, the NASA Artemis moon landing program has been paused again due to Blue Origin lawsuit. So this is a bit frustrating, this one. So just as a bit of a reminder, the NASA Artemis moon program is a program which plans to land people on the moon in 2024. So hopefully in 3 years' time, if all goes well, NASA will be back on the moon. Now, this bit of news is about something that happened back in April. NASA asked a few different companies to put forward their proposals about how to build a lunar lander contract. So SpaceX came up with their idea, Blue Origin came up with theirs, and another company, Dynetics, came up with theirs. Just as a reminder, Blue Origin is the space company owned by Jeff Bezos, pictured here. And last month he went into space for the first time. So they all put in their bids and NASA chose SpaceX. This caused a bit of an upset because normally in these situations, NASA will choose 2 different companies. So that way going forward, they have a bit of competition going for them. And you know, if one of the lunars doesn't work out well, they still have the other one. So Blue Origin and Dynetics were quite upset that they weren't chosen, and they launched an official complaint. And so that caused the NASA Artemis moon program to kind of be put on hold, or at least this part of it. So even though SpaceX was awarded the contract, they couldn't actually start working with NASA on building this lunar lander for quite a few months. And so recently, now that appeal has come back from the office that was looking into it, and they decided, no, everything's good. NASA didn't break the rules. NASA can continue working. So we thought, okay, everything's back on track. But now Blue Origin has launched a new lawsuit. So they're suing NASA again, which again, unfortunately, has caused NASA to pause development on the lunar lander until at least the 1st of November. So yeah, the Artemis moon landing project, the schedules are already very tight. Things have been delayed due to COVID, understandably. And now, unfortunately, things have been delayed again and kind of being held up in this legal red tape. So yeah, we'll see what happens with this, but hopefully things won't get held up for too long. So also in the news, James Webb Space Telescope passes final ground tests. So some of you may know the James Webb Space Telescope. It's been in development for a very long time. You may have heard us talking about it at previous astronomy meetings. Now, this was actually conceived 30 years ago as a successor to the Hubble telescope. And it's planned to be the largest observatory ever put into orbit. But it's been delayed quite a number of times. Initially, it was going to launch in 2011, but it got held back for various reasons, budget, technical difficulties, this thing, that thing. And that launch date kept getting pushed out further and further. But now, finally, there's a bit of good news. NASA has announced that they've completed all of the final ground tests for the James Webb Telescope. So everything's looking good, and it's on schedule to be launched later this year. So yeah, we'll keep an eye out for that, and it'll be very exciting when that goes up. It'll be the largest observatory that we've put into space, and using that, we'll be able to find out more about the galaxy, about distant objects. Now, we've all heard of Jupiter and the Great Red Spot, the Big Red Spot. Well, Venus has a giant dark cloud. So you may not have heard about this. So this is something that came to the attention of scientists last year. But then looking back through records, we've realized that this particular weather formation on Venus has been on there for at least as far back as 1983. So it's been quite a while. And this particular cloud formation stretches 30 degrees north and south of the equator. So in this particular image, you can see how it looks like there's kind of a bulge here, almost as if there's like a big gust of wind kind of blowing the clouds across the planet. And this particular cloud formation, this big cloud, actually rotates around the planet once every 5 days, which is faster than the background clouds on the planet. So that's one of the reasons why this has caught our attention, that we're looking into it further to try to figure out, what's going on here. So this new study, we're still not entirely sure what has caused this formation, but the latest thinking is that it could be caused by something called a Kelvin wave. And this is when there's a wave here on Earth. It can be a wave in the ocean, or it can be a wave in the atmosphere that is affected by something and then causes kind of big weather patterns or disturbances. Here on Earth, a Kelvin wave is what causes the things that we know as El Nino or La Nina. So it's thought that this kind of large-scale weather pattern is also what's causing the so-called giant dark cloud on Venus. Mystery object in space could be a new arm of the Milky Way galaxy. So here's a picture of what we think the Milky Way galaxy looks like. Now, obviously, we don't know for sure because we live inside the Milky Way galaxy. So we can't really go outside and take a photo of what it looks like. This is our best guess of what our galaxy looks like. But now recently, we've discovered a huge filament of gas and dust at the outer edge of our galaxy, which we hadn't really noticed before. This particular curve of gas is about 3,600 light years across. It's about 68,000 light years from Earth. And it's been nicknamed Cattail. And it's thought that this could be another arm of the Milky Way galaxy. So here are the arms that we know about. Each of these spirals we call an arm, and there's 4 main arms. There are smaller arms that come off of it. And so this new one that we've discovered, we're not really sure if it's part of one of the arms that we know about, or if it's a whole new arm. So for the meantime, we've called it Cattail, not really sure what it is. But it's so big that it's thought that it may contain as much mass as 65,000 suns. And this is a bit more of a zoomed in picture of the map of our Milky Way galaxy. So we can see the center of the Milky Way here, this big bulge, and we can see the big arms, the Perseus and, I'm not sure how to pronounce it, Scutum Centaurus, I think, as well as the 2 lesser arms, Sagittarius and Norma. And on the Sagittarius arm, if we follow that around, we can see there's a bit sticking off called the Orion Spur, and that's where we are. And so because we're here, what we see in the Milky Way galaxy, we can get a pretty good image of, things that are within our range of vision, but it's hard for us to look past that big bulge in the center. And the new thing that's been discovered is kind of around here-ish. So we're not really sure if what we're seeing is an extension of one of the existing arms, or if it's a whole new arm. So yeah, we'll see if we find more out about that, but that could help us improve our map of our galaxy. And finally in the news, the fastest orbiting asteroid in our solar system has been discovered. The asteroid has the catchy name of 2021 PH27, and it orbits the sun in only 113 days. So that's a shorter period than any other body in the solar system except for Mercury. So Mercury takes 88 days to go around the sun. This asteroid goes around the sun in only 113 days, which is pretty impressive. It's about 1 kilometer in size. And as you can see, it passes very close to the sun. And it's thought that at the closest point, the surface temperature of the asteroid must reach 500 degrees Celsius. And because of its particular orbit, it's not very stable. It's rather unstable. So we're pretty sure that it will probably collide with Mercury, Venus, or the sun in a few million years. So if you want to go snap a photo of that, you better be quick, because it's only going to be around for another few million years. And that's it for the news this evening. So I'll now pass over to Chris for our main presentation on globular clusters. Over to you, Chris.
Thanks very much. Thanks, Josh. Now I've got to share my screen, don't I? Yep. And bring up this here. Can you see that?
Not yet. Maybe just try that again, or maybe try stop sharing and resharing.
Aha, try this. Ta-da. How about that?
Yep, now we can see it.
Cool. Okay, let's here it is, slideshow, start play. Right, are we good there? Yep, that's good. Have a drink. Okay, so I should be able to let people in. I'll probably get notification as people arrive, but let's get going. Yeah, good evening. Welcome everyone to one of our online talks. So I'm Chris Benton, and yep, we're doing for Hibiscus Coast Astronomical Society online chat about star clusters. So let's get moving. I hope you're all comfortable, got a hot drink and perhaps a cat on your lap. If you haven't, find a cat in the next 5 minutes. So anyway, let's get going. So here you are, lovely, beautiful, starry night, and someone's got a telescope out, maybe a pair of binoculars or whatever, and everyone's getting excited looking at stuff, and everyone knows that you're a member of the Hibiscus Coast Astronomical Society, therefore you must know a lot of stuff. So they immediately start asking questions and carrying on. And one of these young people points up at the sky and says, wow, what a lovely collection of stars up there. That's the constellation Taurus, isn't it? And you go, yeah, how did you know? And they say, oh, look, here's Aldebaran, the eye of the bull, and here's the horns. Can you see my cursor moving okay there, Josh and James? Yep, cool, good. So here's the little cluster looking at, and you think, right, time to get a pair of binoculars, and we'll have a closer look at that for you. So, and that's what they see through the binoculars, and you tell them, isn't that beautiful? It's a very famous star cluster in the constellation Taurus. And then they immediately have some other questions. They sort of say, well, what sort of cluster is it? What's its name? And so on. So the questions are already starting to come out. And then they swing their telescope around to the south to have a look at a nice, beautiful star cluster in Tucana. And they immediately say, oh, this looks amazing. What sort of cluster is this? And what's this cluster's name? And then all the frequently asked questions come out of the woodwork. Why do they differ? What's the difference between those two? How did they form and end up so different? What can those clusters tell us about stars and galaxies? And that's why tonight's talk is entitled Open and Globular Star Clusters. So different, but yet so similar in so many ways, which we'll talk about. The aim of the talk will be to compare and contrast differences between the two different types of clusters, what they tell us, what they've actually got in common. And it's always nice to grab a topic, do a talk, and use it as a vehicle to talk about some astronomical principles. So we'll be doing that as well. So let's keep going. So I've broken the talk into 4 main chapters. We'll have a basic talk about the basic structure of the Milky Way, very brief one. Then we'll talk about open star clusters and the globular star clusters. And then we'll have a summary, in which case we'll talk about our key messages and conclusion. So I am just briefly plug my laptop in so it doesn't run out of power. Okay, so this is what the Milky Way looks like. Milky Way is a spiral galaxy. It has a nice disk with a spiral appearance, looking like this. And Josh has just showed that lovely picture here, looking side on. That's what the disk looks like. You'll see the disk has nice prominent spiral arms going out from them, which we'll have a closer look at shortly. The Milky Way is a decent size. It's 100,000 light years across. And you might say, how big is that? Well, a light year is the distance that light travels in a year. And light travels at 300,000 kilometers per second. So that's the blink of an eyelid. And that is how fast light travels, about 7 times around the world. I'm just going to push the record button on this, but it's gone. Okay, that's fine. Here it is here. So there's the disk here. So it's 100,000 light years across. Now, the distance that light travels in a year, the distance is 10 million kilometers. That's 1 light year. And that is 100,000 of those across. That's just absolutely amazing. So there you go. And you've got all these globular clusters, which we're going to talk about. So here's your disk. Here's the bulge. It's a very super bright, dense part of the galaxy. In the middle, there's a supermassive black hole. It's got about 4.3 million solar masses. In other words, the mass of that black hole in the middle is about our sun, the mass of our sun, multiplied by about 4.3 million. That's amazing. Out here, and this is called the stellar halo around here, and that's where you've got all your globular clusters positioned, which we'll talk about. And then you've got a big dark matter halo around here as well. So that's sort of the basic structure of the Milky Way. Let's now talk about open star clusters. What are they? Where and how do they form? What do they tell us? And we'll use some examples along the way. So briefly, what are open star clusters? Well, they're a collection of stars that are clearly moving together, that are associated with one another. They're gravitationally bound together, where they're unlikely one to shoot off in a direction anytime soon, but they are loosely gravitationally bound. As you'll see, it doesn't take too much for them to nudge off and go their separate way. There's usually just a few number of stars in each open cluster, usually sort of anywhere from 100 up to a few hundred stars. They're relatively young stars. They're usually in the order of hundreds of millions of years old, which in sort of astronomical terms is really young, as a blink of an eyelid. So they're very young stars, just a few of them. They're siblings. because they all formed from the same molecular cloud. We're going to talk about molecular clouds, how they all collapse down to form a family of stars. And all these stars in this open cluster are all part of the one family. They're all approximately the same age, and they're all approximately the same composition and amounts of various elements. The clusters themselves are located in those spiral arms of the galactic disk. They are very readily disrupted, as we talked about. All it takes is for them to perhaps that little cluster to go encounter and go past another gas cloud over to one side, a molecular cloud, or maybe a supernova explosion somewhere. It doesn't take much to disrupt them. And with time, anyway, because of those reasons, and just with time as they move, they get disrupted. And after a few 100 million years or so, they quietly disperse and they go their own way. Our sun would have been part of an open star cluster long time ago. But like all those things, yeah, over a few million years, they slowly disperse and head on their own way. How big are open clusters? Typically, they're up to about 30 light years across, to give you an idea. And as we talked about, that's not a lot, because you saw the galaxy is 100,000 light years across. So these guys are about 30 light years across, typically. Now, the next one, so Pleiades, this is Matariki, also known as Pleiades, also known as Subaru. It's got a few names, it's got a few cultural significances with various cultures, also known as Pleiades. And it's a collection of hot B stars. You know, if you sort of we'll talk about it from time to time, but sort of with stellar evolution, it's the big O and the B class stars, the really big monsters that start blazing away and form first. So the fact is that you've got these hot B stars in there, that tells you that this cluster is less than 100 million years old. They estimate it's probably got about a total of about 1,000 stars in it. It's relatively big. As I mentioned, typically they're about 30 light years across. This is one of the bigger ones at 35 light years across. The fact that those hot B stars are still there, big hot stars, I'll shall show you later on, burn through their material a lot quicker, and they only have very short lives. So the fact that you've got a series of hot B stars there immediately tells you this is a young star cluster. So we know now they form, well, what they are. So where do they form, and what triggers them to form? What triggers that star formation in the cluster to form? Well, as I mentioned, the star formation occurs in the spiral arms, because that's where they are. So there's beautiful, big, colourful spiral arms, that sort of prominent features of the disk, and that is where they lie, and that is where the star formation goes. And that's actually what's a whole talk on its own. But you look at these spirals and you see all these beautiful blues and pinks and stuff. All those colors reflect the processes of new hot stars starting to be born. So as I mentioned, they formed within the disk. They rotate. So you've got these big clouds, big groups of stars and these clouds, and they are quietly orbiting the center of the galaxy, like Ye. And as they go through the galaxy, they also encounter slow-moving regions of increased density and compression. These things are known as density waves, and they are responsible for the spiral arms. You'll probably get the gist of this, but it is a whole separate talk. So there's these little regions of waves of high density and compression that are slowly, also quietly going around the galaxy, but at a much, much slower pace. And these stars and clouds of gas, as they move through, they go into one of these regions of increased density and compression. And this is a good sort of a basic diagram of how it is. So you've got your gas cloud here, or we often call them molecular clouds because they're quite cold. The gas is molecular hydrogen. So as it comes along, usually most stars in the galaxy travel at about 230 kilometers per second. So, they come through here. At what pace do the regions of compression or high density travel? We don't really know, but it's very, very slow. So the clouds and gas clouds come in here, and as they enter into the regions, they start getting compressed from the higher density. The clouds start collapsing, and you get groups of stars forming within that cloud. We're going to talk with a bit more detail, and then slowly the stars move on and you get a nice little star cluster, and we're going to go through that process in a bit more detail shortly. And then the star cluster carries on its happy little way over here, away from this region. Now, there's a good traffic analogy. All sorts of analogies come up. So did one on the weekend, and I like this analogy, where you've got these motor cars here going down the motorway, say 100 kilometers an hour, relative sort of reasonable sort of space between them there. Further down the road, there's a tractor mowing the roadside grass at, say, 20 kilometers per hour. So the cars come road, and as they approach the tractor, this very, very slow moving tractor, the cars all slow down soon and start bunching up and getting closer and closer, much like sort of like a traffic jam sort of scenario there. They go past the tractor faster than the tractor, but a lot slower than they were. So in this case, they were traveling at 100 kilometers an hour. They now slow down to about 50 kilometers an hour to pass that slow tractor. As they get past that really slow tractor that's moving in its own right, the cars start spreading out and speeding up to 100 kilometers an hour. So the analogy here is, here's your gas clouds, here is your density wave, that's sort of high density and compression going on here, gradually moving through the galaxy. The stars and the gas clouds, those big cold molecular gas clouds, they slowly catch up and go through, get all bunched up and compressed as they start going past the tractor in that so-called traffic jam, and then they pass on their merry way and carry on around the galaxy. So that's a bit of analogy of what's going on. And we'll talk about another set, but it's essentially, this is the scenario of this compression and high density of newborn stars and clusters that actually cause the appearance of these spiral arms. So what goes on in here inside these density waves? As I mentioned, star formation starts with the collapse of these big, what they call giant molecular clouds of dust and molecular hydrogen. They're relatively cold. They're in a state of equilibrium. Just quietly, the molecules are just working their way through it. It's all nice and quiet. But suddenly, if something gets triggered, in this case, it goes through one of these patches of high density and compression, you start getting the collapse of the cloud and new stars start forming. When stars start forming, as I've mentioned previously, it's the big, massive, known as O and B stars that start first up, start blaring away. They give out high energy ultraviolet light. And that ultraviolet light then ionizes or bumps off electrons of hydrogen molecules and atoms that are floating around in the gas cloud. And then, of course, what happens is the electrons then come back to the hydrogen and they give off light as they do. So essentially, the ultraviolet light causes the hydrogen to fluoresce. And that's what gives you that lovely, beautiful pink-red color when you see these beautiful pictures. And this is the trapezium collection of O and B stars and the constellation of Orion. If you look in Orion's nebula, M42, very famous, large emission nebula. And that's what's going on. The trapezium is these nice, big, bright stars blazing out ultraviolet light and lighting up the gas and dust, causing it, the hydrogen, to fluoresce. What happens then is those big stars start dying off, and by then the low to moderate massive stars start forming themselves. The light they emit is not as energetic as those big stars. The light that they emit is in the visual wavelength. And of course, that visual wavelength light then reflects off the dust in these big molecular clouds and reflects the light out in a blue color, exactly is what the reason why our skies are blue. The white light and the sort of optical wavelengths from the sun hit the molecules in our atmosphere, and then it gets reflected off those molecules, reflected and scattered, and causes that nice blue appearance. And that's what they call a reflection nebula. And that's the next stage on from those emission nebula, where the big clouds, where the big stars are. The next stage is all the residual gas and dust. You've got a nice big collection, a family of stars, all born from the same clouds, it's the same composition, all roughly formed at the same age. They then blow away all the residual gas and dust in that big original molecular cloud, and you're left with a nice family like this, what we call an open star cluster. And I'm sure a few of you have spotted this already, what star cluster this is. Yeah, it's the jewel box, and I'll show you where to find it. It's up by the Southern Cross. Very easy to see. It's about 100 stars. and it's about 16 million years old. So once again, a relatively small number of stars and young stars. They've only reasonably just formed about 16 million years ago. That is a beautiful, beautiful open cluster. Highly recommended you have a look at it, even with a good pair of binoculars. It looks fantastic. It's called the jewel box because all the stars are slightly different temperatures. So they're all different colors. There's emeralds, rubies, there's all sorts of magnificent colors in there. Do yourself a favor, the jewel box will do the rest for you. So where do you find the jewel box? Okay, so here's your 2 pointers. Here's your Southern Cross. Find the star in the Southern Cross that's closest to the pointers. It's the second brightest star in the Southern Cross. And then just inwards towards the pointers, just a little bit more, and you'll see a little bright sort of star, a little bright spot there. Get out your good pair of binoculars or telescope if you got it. And yep, you will see the jewel box. It looks absolutely gorgeous, and that's where it's positioned. Keep looking at it for a length of time, and your eyes will slowly adapt to it, and the colors will come out to meet you. Beautiful. So this is just a summary here of how stars form and open clusters form. So nice little analogy here. Here is your stars and your gas clouds coming along here. Here's your pressures, and they reach here, this region of higher pressure and compression. It acts like a traffic jam. Everything gets bunched up there. And then as they move out, things get separated again. In our local part of the galaxy, sort of around the region of the Orion Spur, which it's quite good that Josh talked about that tonight, the local clouds and stars around us, our neighborhood, that we encounter a density wave about every 100 million years. It takes about 10 million years to go through it before you go out the other side again. Here's gives you an idea of the velocities. As I mentioned, we travel around the galaxy at about 230 kilometers per second. So here is your nice big molecular cloud before it hits that density wave. It goes into the area here, the density wave. The compression starts collapsing the clouds. New stars starting to form. In particular, it's the big stars that come in first, blaze out in ultraviolet light, ionize or cause the hydrogen to fluoresce. Beautiful colors there, these red crimson colors. Then the big stars die off. The medium stars come along, get born. They give out light in the visual wavelengths. That light gets reflected off all the dust particles in the molecular cloud to cause these beautiful blue reflection nebula. Then you start moving out of this density wave. All the previous residual gas and dust has been blown away, and look what comes outside at the other end. A beautiful, beautiful star cluster. Yeah, the speed there, it's about, you might say, well, what is the velocity? It's about 100 kilometers in this part of the neighborhood. It's about 100 kilometers per second because everything slows down. That's how fast these big clouds of gas and dust travel through one of these density waves. So what do star clusters tell us? Well, star clusters are used to test models of stellar evolution. That is, those models of stellar evolution are based on the laws of physics and what we know about stars, and they try to predict how and when stars evolve during their lives. And they use a lovely tool, which we'll go over shortly. Astronomers use a Hertzsprung-Russell diagram, which is a diagram of what the models describe. And then we'll talk about a color magnitude diagram, which is a similar type of diagram you can do using your observation of the star clusters. And you'll see how these can give a lot of information from star clusters on how good the models really are. So first of all, this is what the stellar models tell us about what happens in the evolution of stars. As I mentioned, the birth of stars starts out in these big stellar nurseries or giant molecular clouds, big clouds of gas and dust, very, very cold. Then you start getting the collapse as they move into a density wave. You get little clumps and little knots of increased density within those molecular clouds. And each of those little clumps or knots then starts shrinking down, contracting down. And that's how you get stars forming. Slowly gets hotter and hotter. It gets hot to the point where hydrogen fusion kicks in at the core of the relevant star. and it's called the main sequence. And by definition, you've probably heard of that term. The main sequence refers to the time period when a star is in its most stable state and it's burning or fusing hydrogen into helium at its core. Stars spend 90% of their lives in the main sequence. It's a very, very stable time. So like all good things, eventually they run out of hydrogen in their core. So what happens then? The core starts shutting down, starts contracting, and you get a small envelope or a zone around the core of hydrogen, and they start fusing that. It gets hot enough, they start fusing the hydrogen to helium in one of the outer cores. And that causes the star to start swelling up. If it's a relatively small star, less than 8 times the mass of our sun, also known as 8 solar masses, then it will start swelling up into a red giant. To give you an idea, our sun when it's a red giant stage, it will swell out to Earth's orbit, to give you an idea of how big these things can go. These red giants, then they go off and the outer layers just puff out like that, called a planetary nebula, and the core, the burnt out core, is called a white dwarf. For these very large stars, greater than the mass of 8 suns, they become red supergiants, even much bigger again. And some of the red supergiants out there, if you put them in the middle of our solar system, some of them would go out to the orbit of Jupiter and even some out to the orbit of Saturn. That's how big these red supergiants are. When these things run out of fuel, they then explode into supernova explosions. If their mass of their core or the original star rather, between 8 and 20 solar masses, their core ends up as a neutron star. If the original star's mass was greater than 20 solar masses, after a supernova explosion, the core ends up as a black hole. So that just puts a lot of terms into context there for you. But the main point here is that stars spend 90% of their time in the main sequence. They then blow up to be big red, massive big giants that are red, and that are very, very bright because they're very large. But what you can conclude from that little sort of thing that we've learned about stellar evolution is that it makes sense that clusters should contain a lot more main sequence stars than red giants, simply because they spend most of their life there. Now, this is the Hertzsprung-Russell diagram, and it's a very useful tool, as mentioned, and it describes how stars go through their evolutionary stages and how we should observe them. And what the astronomers do on the x-axis of this graph, they've plotted the temperatures, the surface temperatures of stars, like down here, 3,000 degrees. Any star in this line here is 3,000 degrees, up to 6,000, 10,000, up to 30,000. Our sun sits here. Our sun surface temperature is about 5,800 degrees. So that's the x-axis. On the y-axis, they plot the luminosity, or how bright a star is, or its power output, also known as its luminosity in there. And when you get as many stars as you can, you start plotting them and see where they fit in there. And the models of stellar evolution predict that different star types and different stages of evolution should predominantly be observed in separate little groups. And they describe the main sequence stars should go up in a nice little thin band up here from right to left, bottom right up to top left, and the giants should form a nice little group here, and the supergiants up in here. So that's a model of what stellar evolution, or the models of stellar evolution say we should look at, should we plot them like that. So the other thing that models also predict, and I mentioned this at the beginning of the talk, is these big massive stars have much shorter lifespans. They've got more mass, so they have more mass coming down with gravity, so they get higher temperatures and pressures at their core, so they burn through their hydrogen a lot quicker. And you'll see here, these big O and B massive stars, they spend, which is 90% of their life on the main sequence, it's only 4 million years, as opposed to our sun is expected anywhere between 10 and 12 billion years it'll spend on the main sequence. So you can see, look at the difference. Huge difference. I think there's about, 3,000 times. Our sun's going to live for about 3,000 times longer than perhaps one of these O and B stars. And that's something that astrophysics models has predicted. So therefore, you'd expect, if you're going to make some observations of the sky out there, what you're going to find is that clusters should contain many more smaller stars and fewer larger stars, because once again, main sequence stars are that little bit smaller. It also, because these smaller stars, look, they're living so much longer. They're living not only actually from last the talk we did, you'll probably find out that the nature also has a tendency where it prefers to produce lots and lots and lots of small stars than just a small number of big stars. So you almost put them in like a pyramid. For every one big OB star, you get zillions and loads and loads and loads of these little tiny red dwarfs. But you'll see down here, these low mass stars, they spend up to 700,000 times 10 to the 6, as opposed to 4. So they spend so much more longer time. So it makes sense. You expect to see lots and lots of more smaller stars and fewer larger stars. You'd also expect to observe that the younger star clusters are going to have more massive stars than the older star clusters, because the bigger stars that burn out quickly in a younger cluster, they wouldn't have had time to burn themselves out, as opposed to, say, a medium-age star cluster. You think, well, the big, as I alluded to in one of those early slides, by the time all those middle stars come, the big stars have been and gone. So those are observations that you would expect to see from the astrophysical models of stellar evolution and what we think in theory should be happening inside of stars. So it makes sense, if we've got these models, test the models out. And what do they do to test them? They use, star clusters, open clusters here. So they plot these things called color magnitude diagrams of clusters. And these are very useful tools. Now, you might think, oh, this is all different. It's exactly the same principle as that Hertzsprung-Russell degree, that diagram. And what they've plotted here is they get little light filters, little bit that collect light in certain bands. And the B band, for example, is the blue end of light, visual light. The V is bang in the middle of visual light, little narrow bands. That's the range of sort of wavelengths of visual light, optical wavelengths. The V might be in a small little band in the middle and a blue little bit off to the higher energy ones at the blue end. So if you get two filters, you measure how bright a star is in two filters, subtract one from the other and get the difference. That's called the color index. And the color index quite nicely reflects the temperature of the surface of those stars. So all you need to do is plot or measure how bright all the stars are in a star cluster, in the B filter and the V filter. You separate the difference, put their color index on here, and up this side where you had luminosity for the y-axis on the Hertzsprung-Russell diagram, you just pick one. For example, this one here, they've picked the V filter, and they've just put how bright stars are here. Now, you might say, aha, but isn't that just apparent brightness? Because you're not actually measuring the real true luminosity, how bright those stars up here. But the key, and this is the key to it all, of these star clusters, all the stars are all sort of a collection of stars, all lumped together in that same cluster. All those stars are effectively the same distance from us. So you just have to take how bright they look here from Earth, what they call the apparent magnitude, and that automatically transfers on and reflects beautifully their absolute, or how bright they really, really are. So instead of luminosity, you just put the brightness of one of your filters here. Instead of temperature, you don't have to measure the temperatures, you just put the color index here, and you get that same graph. Now, these color magnitude diagrams are very, very useful to provide information for you on the cluster itself, and also to test and put constraints on the models, to tighten the models up and make them better. So what sort of information? You can get a lot of information, but the two classic ones you get from one of these color magnitude diagrams is the age of the cluster, and also the distance. Because you might wonder, well, how do they work out how far away these clusters are, and how do they work? How do they know that that cluster is 100 million years old, or that one is 2 billion years old? How do they know? They do a color magnitude diagram, because we've learned at the principles how these big stars start dying off, and as the stars get smaller and smaller, more and more of them are going to start dying off. So here is your main sequence stars running up that diagonally up here. Here's your red giants going off, and you'll see where the stars have this mass have started evolving off the main sequence. So that point there is called the main sequence turn-off point. And so you can probably get the gist of it here. If you work out where that main sequence turn-off point is, and you can tell here from the color index what temperature those stars are. You look up and you find out how big the stars are expected to be at that particular surface temperature, and you then work out from those graphs that I showed you earlier on, those charts, you then work out from the charts the models of how long those stars spend on the main sequence. For example, if that was a G2 star, which is the same as our sun, and you saw that going off, we know that the sun would spend about 12 billion years on the main sequence. And if that turn-off point is where a G2 sun star, which is our sun, is right on that point, you know that star cluster is roughly about 12 billion years old. How about how far away it is? Well, once again, you look at the turn-off point, you look at what sort of temperature of the star is, or what they call what spectral class it is. You then can work out from there, from the charts, you know how bright, from the models, how bright that star really, really is. You already know how bright it looks from Earth, and there's simple little formulas you use to separate the distance between how bright something genuinely is to how bright it looks here. It's called the distance modulus, and it's a nice little simple formula. But the point is, you just draw a color magnitude diagram like that, and you look where you can see the stars starting to head off the main sequence. You can very quickly work out the age of the cluster and its distance. I actually do a whole talk. If you think, oh, that's a bit to take in, don't worry about that, but you got the gist of it, the principle of it. I've got an entire 1 hour talk just on color magnitude diagrams, but I think you've got the gist of that there. So yeah, you can actually go forth and test your models, astrophysical models, by things that they start looking at here. The width of the main sequence band. On the main sequence, stars do move around a little bit. They start looking at where you're seeing a few stars out here, more over here, and they match it up with the models to see that it's right. And if it doesn't fit, they know they've got to tighten their models up. They haven't got things quite right. And I can tell you right now, stellar evolution models have been so successful, almost exactly as they've predicted. They put their telescopes on, start measuring with their filters, measuring and drawing these color magnitude diagrams, and they're actually not too far off the mark. Other things they can predict, star formation rate. They can tell that by looking at the numbers of stars at different places along the main sequence. So they can work out the star formation rate of a cluster, how quickly its stars formed many millions and billions of years ago. The IMF stands for initial mass functions. They can tell how many small stars and how many medium and how many bigger stars would have been in that cluster originally. And of course, here's your red giants, and they check that the red giants that they see are in the correct proportion to the numbers predicted, and usually they are. So you can see how this color magnitude diagram, it's so easy to draw up. All you need is 2 filters on your telescope, pick each star out, measure how bright they are, plot them on this nice little graph here, and you can work out a lot of information about the star cluster, but you can also test your own models of stellar evolution, which have been successful. So that's open clusters. So how about globular star clusters? What are they? How do the stars move around inside them? Where are they located? What do the color magnitude diagrams look like in globular clusters? And where and how do they form? And we'll use some examples along the way. So, as opposed to having a small cluster of young stars loosely gravitationally bound, globular star clusters are much larger. And this is 47 Tucanae here, the second brightest globular cluster in the sky. As you can see, that's 120 light years across, as opposed to what about 30 was your typical one for open clusters. So they're a lot bigger, they're more compact. Instead of just up to a few hundred stars, you've got up to millions of stars in globular clusters. Instead of being really young stars, these are really old. Some of the oldest stars in the universe are in these globular clusters, and they're all tightly bound into the spherical shape. So it takes a lot to start pulling these stars apart, as opposed to, remember, the open clusters, they just go past another cloud. Oh, they get distracted and they slowly get disrupted, and after a few million years, they slowly disperse. These clusters have clearly kept together in one nice tidy unit for billions of years, so they're much more stable. So these are your globular clusters. So you can immediately see an obvious difference. These are different beasts. So how do the stars move around in these big spherical things? There's three forms of movement. One is circular, so you get some stars in these globular clusters that just simply go round and round, orbit the center of the globular cluster in a nice sort of circular orbit like that. You get some that just go straight lines, just up and down, and you get other stars doing that as well, up and down, crossing through the middle of the globular cluster. And then by far, most of them do what we call highly elliptical steep orbits, whereby they, if that's the point, that's the middle there, they go zooming in, zip around the middle of the cluster and back to the outer bits again. And then you might get another one out here going through doing it at all different angles and orientations, but highly elliptical orbits that come way up from the outer skirts of the globular cluster, come zipping around the center of the globular cluster and zip back out again. You imagine that going on from all directions and planes and orientations. It's a good analogy. It's like a beehive, just bees buzzing everywhere, except you got stars, millions of these old stars just. So it makes sense. In the middle of these clusters, there's a high incidence of collisions, because you might think, God, that must be craziness in the middle. It is. There's loads of collisions that occur in the middle of these, in the central regions of these clusters. So where are they located? Primarily, they're seen in the stellar halo. So here's that original diagram that I had. Here's your nice big bulge and your supermassive black hole in the middle. Here's your disk with the spiral arms going through it. And here's your stellar halo. It's all this region here out in the stellar halo that you see the globular clusters. In comparison, remember the open clusters were all getting formed in the spiral arms in these disks here. So that all the open clusters are all located in that nice little plane of the disk, and the globular clusters are scattered all around here. There's over 150 globular clusters that they've already identified. There, as Josh mentioned, you can't see through the main sort of the central bulge. So if we're here, we're having difficulties looking around over here. So we can't see it all, but they estimate quite most likely there's going to be up to about a couple of hundred globular clusters in the Milky Way galaxy. So what is the color magnitude diagram? This is your typical one. This is from M68, nice globular cluster. It's 11.2 billion years old, and it's 34,000 light years away from us. How do we know that? You know how we know that. They've plotted the color index here against the how the apparent brightness. Here's your main sequence, and notice how your turn off is a lot lower down, because the big massive stars would have all died off up over here, but you've had more time where a lot of these medium mass stars have also had time to burn out and go off the main sequence and become red giants. So that turn off point is much, much lower down than the open clusters. You use your formulas as we talked about, or we can go over with another talk again, and you can work out that it's actually 11.2 billion years old. So that's really the main difference. And notice here, you've got more stars going on. Look how big, thick the main sequence is, and all these red giants going on here. Notice there's more stars, and once again, that reflects the globular clusters. So the big one is more stars by far, and a bigger, thicker main sequence, which has got a lower turn-off point. So how and where do globular clusters form? Well, the bottom line is it's poorly understood. It's been a mystery for decades, for centuries, in fact. How do these things, why are these things there? Why are they so densely packed? Why are they so big? Why are they out in the halo of the Milky Way? What put them there? Why are they there? How did they form? Most likely from what we call superclusters, which means, essentially huge, big clusters, massive, dense star clusters, some possibly the remnants of dwarf galaxies, smaller galaxies that orbit the Milky Way or their host galaxies and then slowly get absorbed. So let's delve into that a little bit more deeper. Why superclusters? So let's talk about what we observe and what we hypothesize about superclusters. So we know, what do we observe? We observe there is no active star formation in globular clusters. Star formation is long gone over. It's just a big, dense, compact sphere of old stars. No dust, no gas, no star formation. Typically, they're the oldest objects in the galaxy that you see. So that's what we observe. So what do we hypothesize and think about all of this? We think probably, most likely, globular clusters are among the first collection of stars to have formed in the universe. The conditions in the early days of the universe would have allowed large, dense clusters to form. The early universe was a lot smaller, it was a lot denser and more compacted itself. So it would have lent itself for when a star cluster formed, those star clusters would have been much, much larger and much denser. So the conditions were more ripe for that to have occurred. The other hypothesis is that probably superclusters may well be the precursors to globular clusters, because you've got globular clusters with so many old stars. Where did they probably come from? Probably from these super dense, large superclusters in the early universe. So that's what they think from what we observe. And to give you an idea of what these superclusters look like, Westerlund 1, that is a young supercluster. So very rare, a young supercluster in the Milky Way. It's about 6.5 light years across. It's 3.5 million years old, so it's a young one. But it has, if you gather up all the stars and weigh them all, the total mass, 63,000 solar masses. So remember I said the average open cluster is sort of, got in the order of, 100 up to a few hundred stars. Well, this here, you can't count the number of stars, but its total mass is 63,000 times the mass of our sun. So it's a young supercluster, very rare. It's called Westerlund 1. And the general speculation is that it probably will evolve into a globular cluster. But of course, that's going to take millions and millions and millions of years to occur. So we won't stick around for that. So how about, so we can understand, you think, I can understand why they think they're from superclusters. What do they think that may be the remnants of a dwarf galaxy? Well, it's this guy here, Omega Centauri. There's always got to be someone different in a group, doesn't it? Omega Centauri is the largest globular cluster you can see in the sky. It's a whopping 172 light years across. It's large. It's got about 4 million solar masses. It's about 11.5 billion years old. I'm going to show you where you can see that. It's in the southern sky. You can see that with, actually, it's a point of light. You can see it with your naked eye, but it looks great through a pair of binoculars or a telescope. So it's interesting because your average globular cluster's got the population of stars, 1, maybe 2, sometimes 3 different populations of stars that have just been, obviously a little bit of star formation has been at slightly different times. But star populations with Omega Centauri has a huge range of stellar ages, a range of metallicities. Metals refer to elements that are just heavier than hydrogen and helium. So if you see something with a higher proportion of metal elements in it, it means that star is a 2nd or a 3rd generation star, because stars tend to produce those elements as they go along. Bit of a long story, but the bottom line is stars of different age groups. There's multiple populations of different age groups in Omega Centauri. The other thing is retrograde orbit. If most of the globular clusters all orbit the galaxies with a certain type of motion, Omega Centauri does the opposite. So obviously something else has put it there. So they're wondering whether there was many billions of years ago, there was a dwarf galaxy out there, and slowly it got trapped and went around and got absorbed into the Milky Way. And what we're looking at here is the old central core of this very small dwarf galaxy that the Milky Way has captured. So they think probably at least Omega Centauri is probably the remnant from the core of an old dwarf galaxy. Here's how to find it, really is. So here's your, once again, here's your Southern Cross here. Here is your 2 pointers. Here is the star that's closest to the pointers. And remember that the open cluster, the jewel box is here. So while you're there, that's just with a good pair of binoculars too. You get equals distance, just what we call star hop, equal distances. So star hop, so jump and get an idea of the distance you move to the first pointer, then go straight up like that, the same distance to the next star, and then go straight up the next distance again to that star. It's called star hopping. And that's a very easy way to find Omega Centauri. You can actually see it with your naked eye, as I mentioned. That is so cool. So you've got the largest globular cluster in the sky that you can see there with a good pair of binoculars or a telescope. And right next door to it, you've got certainly the most beautiful open star cluster, the jewel box sitting right there, which you can also see with a nice pair of binoculars. So how about the new supercluster model? So they're constantly with computers and simulations trying to work out how things would happen and how these globular clusters might have formed. And there's a very new model, computer simulation model, that's looking very, very attractive. And let's have a look at it. So the background behind the model is that globular clusters likely formed in compact regions of star formation. That were really compact, because look at them themselves, they are so compact, millions of stars just jammed really into dense packages. So most likely globular clusters formed in these compact regions. We also know, as a bit of background, as we've alluded to, the extreme conditions were ideal in the early universe. The universe was a lot smaller, so gas pressure would have been higher. Everything was more dense and crammed in. So it was just the conditions in the early universe were extreme, and they were just ripe for these big, large superclusters to form with millions of stars. As we talked about superclusters, they have millions of stars in them. The conditions were perfectly ripe, and almost certainly globular clusters formed in these sort of regions. So that's a bit of background around it. The other thing I'll mention here, a little property about globular clusters. I said how they are stable, and yes, they are reasonably stable, but there are three main processes that can gradually gnaw away and dissolve them. The first two just to a minor degree, and the third one to a much bigger degree. So the first one is that there's a principle. If you get any sort of spherical grouping of objects and that all gravity's holding them together, the bigger something gets, the stars, or whether it be gas or whatever it is made of, that object, as you go further and further out away from the center, the gravitational hold or attracting of those objects way out is getting less and less, and you're more likely to lose them. And a good example of that, you get these big, massive stars, that are huge, sort of 80 plus times the mass of our sun. They are so unstable because the gas, hydrogen and the gas way out in those distant parts of those stars is so far away from the center because the star is so big that it doesn't have a proper hold on the star, and those outer layers just these stellar winds just blow off, and the outer layers of the star gets blown out into interstellar space. So there's a principle: the something bigger something gets, the less good they are at holding those outer objects together. So now dying stars, so I'm referring, remember that slide I showed you about stellar evolution, how stars, low to medium-sized stars slowly puff out into planetary nebula, so the material just gently puffs out, and supernova explosions for the heavier ones that just go boof and send all the material out into space. So it makes sense that these dying stars, as they expel the material, that material gets puffed out into the outer parts of the globular cluster, which in turn expands the globular cluster, which in turn means a lot of those stars in the outer parts of the globular cluster, the gravity holding them together is weaker and weaker, and they start getting less stable further out, and some of those stars just start to wander on their way, like the open clusters did, the whole cluster. But these outer stars, yep, they can quietly wander on their way. Maybe there might be a supernova explosion over there, or maybe a little gas cloud might go past, and and away they go. So that's one reason why you can slowly start dissolving away globular clusters. There's another one. As I mentioned to you, stars are going in all directions and slinging around one another, and there's a lot of interactions going on, and one star can speed up and slingshot the motion of another star to the outer parts of the globular cluster. So stars can pick up speed. NASA does this with gravitational assist. It might get a spacecraft that wants to go out to the outer solar system. So they head to Jupiter, swing around it and get some gravitational assist and speed the velocity up. It's the same with these stars in the globular clusters. They're all swinging around and interacting with one another. And it makes sense. Some of these stars get gravitational assist in their velocity, and slowly they start heading further and further out away from the center of the globular cluster. And that same principle applies. If material gets further and further out, it loses its ability to hang on tight to the globular cluster as a whole. And that's another reason slowly the globular cluster can get dissolved and get eroded away. But the big one by far is when you get a globular cluster, and if it happens to go past a really big, thick, dense gas cloud, or goes through, say, the disk of a galaxy, where there's a lot of what we call gravitational tidal forces, where the other object they're going near or going through will pull and tug at them and start elongating and start tearing away at it, and pulling stars away from it. And that's by far the most common and most efficient way to tear apart a globular cluster. So they're not exactly totally bulletproof. They can slowly get dissolved. So that's a little bit of background, with these, when they're working through these models of what makes globular clusters tick and where could they have come from. Those are some important little sort of principles to keep in mind. So let's go to the model itself. So the early compact, small, dense, complicated universe was full of dense galaxies that were gas rich. There was a lot of gas in these really dense, compact galaxies. And it makes sense from them. Lots and lots of star clusters formed, and they probably formed in various sizes, from the really small clusters right up to the really, really big super clusters. Just a lot went on. It was pretty chaotic in the early universe. Because of the crowded environment and galaxies were smashing into one another and pulling and each other apart, the smaller clusters, well, all the clusters were subject to a lot of tearing and ripping from these tidal shocks in these crowded environment, but the small clusters were more vulnerable and they just got totally decimated. And it was the larger, big super clusters that managed to survive those turbulent times. And to the next stage then is that with ongoing galaxy collisions and mergers, slowly galaxies started evolving, and you started getting these spiral galaxies in with these nice disks with globular clusters scattered throughout the disk. But also with all the toing and froings and the collisions and mergers, the dynamics that were going on caused a lot of the globular clusters in the disk, a lot of these central globular clusters got ejected out into these outer stellar halos out here. So all the clusters would have formed in here. The small ones got decimated. With further interactions, the biggest surviving clusters got biffed out into the stellar halo, where of course there were no more interactions. Things are pretty quiet out there. And of course, as the universe evolved, it got less and less chaotic. There was less interactions between galaxies, because you look at distances between galaxies now, and you're talking millions of light years between galaxies. Our nearest galaxy, or nearest large galaxy, Andromeda, is actually 2 million light years away from us. So there's huge distances, so you're not getting these collisions. The galaxies now are relatively stable, but the globular clusters from early days when it wasn't so stable got biffed out into the stellar halos, and they're still sitting there to this day. So they have remained in that stable halo environment to survive billions of years, and that's why you see them as they are today. So it explains today's galaxies, how today's galaxies are certainly much less gas going on because they've already formed a lot of stars and so on. They've got the small open clusters still form, but they're now only small clusters because there's not so much gas floating around, and they form in that nice disk. And it also explains why galaxy collisions and mergers are less frequent, as I've mentioned. So the clusters quite happily remain, the small open clusters remain in the disk. And of course, the globular clusters remain in the outer stellar halos. So the conclusion is that globular clusters, as different as they look to those open clusters, they actually just may be a natural outcome of regular standard cluster formation in the early universe. So they both actually exactly the same things going on, but just the smaller ones got decimated. The bigger ones were just biffed out into the halos. They're stable out there. They're formed into globular clusters. We still get open clusters in the disk today, but of course they're a lot smaller. But the bottom line is they probably, just from regular star formation, they all came from the same roots. So some of the key messages from tonight's talk is open and globular clusters are so different in so many ways. Open clusters are groups of young stars loosely gravitationally bound together in the galactic disk. As opposed, in contrast, globular clusters are much larger, much compact and dense groups of old stars tightly gravitationally bound, and they're sitting out in the halos of galaxies. So you can see some big differences. They're definitely different. But on the other side of the coin, they've got a lot of similarities. They've got a lot in common as well. Within each cluster, The stars are usually a very similar age and they're all of the same distance to Earth. Both types, for that reason, act as galactic laboratories to test theories of stellar evolution. And the third one is, open and globular clusters maybe just be two extremes of exactly the same object, just in exactly formed through exactly similar physical processes. Just different things over time have happened to them and put them in different places and made them look a little bit different. But they're just two extremes of the same object, formed through the same physical processes. So I hope that brings together differences and the similarities, what they've got in common. So I hope you've enjoyed open and globular star clusters, so different, but so similar. Thank you. Now, question time. James. Have I got any questions in there?
Okay.
Here's one from Jonathan.
Jonathan.
Thanks. I've just brought up the chat room. Thanks for a very interesting talk, Chris. Can you tell us, do other galaxies have globular clusters? Yes, they do. So I use the Milky Way as a good sort of prototype of spiral galaxies and stuff, because it's our home galaxy. Obviously, that was a good one to start with. I always carry slides with me of outtakes. So let's have a look at the outtakes. Just going to get rid of that for a sec. I did prepare some slides on that. They certainly are. Most galaxies have globular clusters around them. That's spiral galaxies and elliptical galaxies and even irregular galaxies. This is M87. It's a giant elliptical galaxy in the Virgo cluster. And that's got, I can't see it, but I think it's got about, what do I see down there? It's got thousands of globular clusters that are attached to the M87. So yes, they're found in most galaxies, spiral and elliptical, and even irregular galaxies. That both the small and the large Magellanic Cloud has globular clusters. And there's a beautiful big globular cluster in the central bar of the large Magellanic Cloud sitting right there as well. So yes, Jonathan, all galaxies, spiral galaxies and elliptical galaxies and irregular galaxies, globular clusters are very common in all of them, which would tie in with that theory as well. Okay, any other chats there? I don't think we've got any other questions.
It doesn't look like it. There's nothing on YouTube.
Yep. Oh, good. Okay, so it's good.
So I've got a question for you though, Chris.
Yeah.
Which are your favourites? Open clusters or globular clusters?
Oh, look, I'd probably say open clusters because they've got more variety. Like you got the jewel box, all the beautiful colours. They do vary a lot in size. You've got the wild duck open cluster, which is that's probably the most massive one. That's huge. And then also you get them how, as you probably got from my slide there, it's a continuum from a giant molecular cloud to an emission nebula to a reflection nebula to an open cluster. It's a continuum, and it's really neat how you get these objects in the skies that have got a little bit of everything going on. You can see the open cluster starting to form. You can see the reflection nebula. You can see the emission nebula. So sometimes you get all three in one sitting. In one object, you can see the whole thing evolving. So for that reason, I like the variety in color, size, and just the characters of open clusters. But that's notwithstanding how beautiful globular clusters look too. How about you, James? What's your favorite?
I think everyone knows the answer to that one. I like the globular clusters myself.
47 Tucanae.
Yeah, 47 Tucanae, and my favorite, of course, is Omega Centauri. That's my number one favorite. Yeah. Purely because most people don't even realize that it's there. It's so big. As you mentioned in the talk, you can see it through with your naked eye if it's dark enough. It sits there about the size of a full moon, so it's a pretty large thing. Yet most people go their lives and they never ever see it. And then once you discover it, it's one of the things that you sort of automatically look to and go, there's a globular cluster. I can see it with my eye. And that's pretty much why I like Omega Centauri in particular. Then 47 Tuckers is the second one. It's so big, it's in the sky. You can see it with the naked eye, but most people don't actually see it because it's just so faint.
Yeah. It's pretty cool. They're all cool, aren't they? So yeah, and I can certainly see why you like those. Okay, any other questions, folks? No.
Are there any other questions on the YouTube side?
Yeah, otherwise we'll continue to try and have these every 2 weeks. We had scheduled one of the professor from the university was going to come up, so we've just postponed, and we're still going to all those little things we had lined up, we'll still do those after lockdown. But in the meantime, we'll try to. We can't promise every 2 weeks, but we're going to have a good crack at it anyway. Of every 2 weeks, a talk online, just to keep you busy with stuff. So we'll do our best to keep up with that. We just can't make any promises, but we'll aim to. Any other comments?
Just keep an eye out on the Facebook group and email, and we'll keep you informed as to what's going on.
All good. Okay. So we say good night to everyone. I hope you finished your cup of Milo and you've had a cat on your lap, and hope you have a good night. Thank you.
And of course, we did notice your beautiful mug there, Chris.
Aha. And the other thing, my Superman cufflinks. Can you see those?
No, not very clearly. If you take your screen sharing off, it will make the video big. There we go. Nice.
Yeah, I got given it by a very good friend, a stop share. Oh, no, that's it. How's that?
Yep, much better.
So there it is there. That's a very good friend gave me those. My little Superman cufflinks. I wear them when I do my talks online while I'm drinking out of my Hibiscus Coast mug.